Hello, good evening everyone. This is Manjit, the TA for this course, Nature and the Properties of the Material. Today we will discuss the assignment number 6 for this course, which is taught by the professor, and we will cover the 15 question or the 15-16 question of this assignment. We will do one by one, and let's start it. So is it visible? So, mm, okay. Okay, so this is question number 1 of the assignment number 6. Here it is asked, identify the name of the MER unit shown here below, also the category of it. A is the polychlorofluoroethylene, second is the thermoset polymer, and another is the polychlorotrifluoroethylene, and D part is the thermostatic plastic. Thermo thermoplastic polymer. Here you we have to also we have to tell about the MER unit, that is the smallest unit of the polymers, and the also the category in which they are the lying. So basically we have the two category. We have two category. This is the one is the thermoset polymer, and another is the thermoplastic polymer. So we will discuss these two first, and then we will continue to discussion. So if I'm talking about that, this is my, so what will be the comparison for the for the thermostat and the thermoplastic one? So thermoplastic polymer one is, and another is the thermoset polymer. Okay, if I see this in the thermoplastic, if I give the heat to this material, this polymer, it gets softened when it is heated and hardened when we cool it. But in the thermostat, this is not the scenario here. This become harder when we heated it. So this process in the thermostat is the irreversible process, and this is the reversible process because it will get softened when we heat and it become harder when we cool. So we can change to this to any kind of the shape, to any shape, size, but this can't be molded into any shape and size. Okay, because this is the irreversible. This become the permanent. So this will not change. And if I talk about the molecular structure in both the category, in molecular structure, this thermoplastic are having the linear or the branched chain with weak intermolecular forces. But in the thermostat, this is cross-linked network, and they are having the strong intermolecular forces, or we can say that with the strong covalent bond. Okay, so this also, because these can be molded to the into the any shape, and this can be remade also. So this is less resistant to the high temperature. This thermoplastic is the less resistant to high temperature and the chemical as well. But this thermoset is highly resistant to heat, chemicals, and deformation. Okay, so that's why this is less resistant to high temperature. So it is used in the packing. Poly thermoplastic basically used in the packing, plastic bottles, toys, or any kind of consumer goods. And then this thermoset polymer is used for because it is highly resistant to the heat. It will not change. So it is used as a electrical insulation, adhesion, or the coating. As their name suggests, thermoplastic. Plastic, we know that it get melt when we heat and it get harder when we cool. And in the thermoset, it will upon heating thermo is basically mean the heat and it will set when we heat it. So these are the two type category of the polymer that is more popular, that is the thermoplastic and the thermoset. And if I take the example of these one also, so example for the thermoplastic will be the polyethylene, polypropylene, PVC, we know the polyvinyl chloride and PTFE also. And if I talk about the thermoset, you know about the epoxy and resins that we use for the electrical insulation or the for the adhesion. So the epoxy, resins, etc. are the thermoset polymer. So these are the two type of the category of the polymer. One is the thermoplastic and thermoset. Now here it is given this this carbon. This is the structure of the poly, because this is only the mer unit, so this will be get repeated. So the if I am talking about, this is only the mer unit, so polymer will be of the end time of this one, because in the polymer this is the repetition of the mer unit. So this is the my we have this is the trifluoro, and there is one chlorine, so the one chloro and trifluorine, and because of the double C here, so ethylene. So this will become, this mer unit has the name that is poly, and it is also for the naming of this polymer is according to the IUPAC number, that is there is some criteria that you have to follow for the naming of the any polymer, that the naming of the chemicals or that. So this will become this is the polychloro trifluoro trifluoro and ethylene. So the mer unit is the polychloro trifluoroethylene. That is your trifluoro. We have the three. In the first, it is saying that the polychlorofluoro only. There is no tri, because we have the three fluorine here. So it will be the three fluoroethylene. So C is the mer unit of this one. This shown a figure of the figure that is shown here. And what will be the and in which category it is belongs to? That will be the thermoplastic one, because we have written here the example for the thermoplastic are the polyethylene, polypropylene, PVC, PTFE. This is the same thing. So the category in which it is live will be the thermoplastic polymer. So C and D are the correct answer for this one, this question. Okay, so first start the naming of the figure that we can see from the ethylene, because ethylene had the ethylene basically as the name suggests, it is for the two carbon, and there are the three I mean fluorine atom are attached to the carbon. So this is the three fluoro and one is chlorine. So chloro, and because of this is the mer unit, so there will be the I mean repetition of these mer units. So this is the poly chloro trifluoroethylene. Okay, and you can know this is the PTFE. So this belongs to the thermoplastic polymer. Okay, let's move to the next question. Question number 2. So the side group in the polyvinyl chloride are. What are the side group of the polyvinyl chloride? Because the what is the polyvinyl chloride? This is the what is the first, what is the vinyl chloride? Vinyl chloride is C double bond C H. There is only one chlorine attached here. So this is my vinyl chloride, and if I take the mer unit of this one, that will give you the polyvinyl chloride. So the corresponding mer unit, the side group or the polyvinyl chloride will be the C bond C H H hydrogen and the chlorine. So this is the polyvinyl chloride and we call it PVC also. So what are the side group in the polyvinyl chloride? Because this is 3H and the 1 chlorine. So B will be the right answer because it is having the 3 hydrogen and the 1 chlorine atom. Okay, is it clear? Okay, let's move to the next question, question number 3. In question number 3, it is asked here the factor that promote non-crystallinity in the polymer. So what are the factors that are promoting the non-crystallinity in the polymer? Because polymer are the non-crystalline in the nature, but what are the factors that are responding to this one? So non-crystallinity is basically a, or it can be, I mean it's not necessary, it's can be due to of these one of the factor that maybe they are having the irregular molecular structure, because crystallinity, in crystallinity we have the regular pattern or the regular arrangement of the atom, but in the non-crystallinity it is the random arrangement of the pattern. So this non-crystallinity can be due to of the irregular molecular structure. It can be due to of chemical composition. It can be how because of the different kind of these side groups in the mer units. So this can be one reason for the non-crystallinity. Another, it can have the chain flexibility. If they have the chain flexibility, so one of the reason can be the chain flexibility, or the plasticizer that is we added in the mer unit, that also give the flexibility or the non-crystalline nature to the polymer. Plasticizer, thermal history. Thermal history in the sense, if we heat and then we cool down, we suddenly cool down that mer unit, then there will be the non-crystalline nature of that, because it, if it is taking the long time, or if it is stabilizing with the time, I mean without any giving any pressure, or if we are kind of subjecting to the just to cool down in some time, so that will give you the non-crystalline one. So thermal history also affect your non-crystalline nature. And the molecular weight, so one can ask how the molecular weight can change the crystallinity of the polymer, because molecular history is if my molecules is having the high molecular weight, it means they have the high degree of the non-crystallinity, and because they are high degree of non-crystallinity, because they are having the more entanglement, means they are the less mobility, and that making that preventing your the to make the regular pattern. So that can be also a factor of the non-crystallinity in the polymer also. So if we see the option given here, that is one is the large random side group, yes, because the presence of the chemical composition, as we said, so large random side group can give you the irregularity in the polymers, that also give you the non-crystalline nature also. So yes, this is the one of the example. And the branching, yes, branching make the more flexible the polymer, also that will be not the periodic one, so this will also give you the non-crystalline nature. In the C part, the addition of the plasticizers, yes, we already uh, uh, told this thing. The addition of the plasticizers are also give you the non-crystalline nature. And the copolymerization. What is the copolymerization? Copolymerization is basically the process. It is the process where two or more different monomers are combined to form a copolymer. So if the two different kind of the monomers will be mixed, I mean they are combined in such way, that also give you the irregularity in your pattern. So that will lead to the non-crystallization in the polymer one. So this copolymerization is also the one of the factor for that promote the non-crystallinity in the polymer one. Okay, so your non-crystallinity in the polymer can be due to the irregular molecular structure, that can be also the chemical composition, or we can say the large random side group. Branching also, it can be due to of the addition of the plastiger, also copolymerization also, chain flexibility or the thermal history, how we have heated that one, or the molecular weight also. Okay, this is the molecular weight, not the history one. Okay, so this will give you the non-crystalline nature. So let's move to the next question, question number 4. Okay, in the question number 4, it is asked the weight in the AMU of a polyethylene chain with 1000 mar is. So we know that what is your polyethylene chain? Polyethylene chain is the CH2 bond, CH2. This is, and now this is the polyethylene. Now your N, it is here is the 1000 mass. There are the 1000 repeating unit of this ethylene. So first, if we have to calculate the weight in AMU, if somehow we can calculate the weight of the this ethylene one, so I can calculate the weight of the polyethylene chain. So what will be the weight of ethylene? Will be the, we have the two carbons, so 2 into atomic mass of the carbon will be the 12 plus how many hydrogen it here are, that are 4, and mass of the hydrogen is the 1 AMU. So this is giving you 24 plus 4, that is the 28 AMU. So the weight of the ethylene is the 28 AMU, and we have the 1000 mar units. So the total weight of the polyethylene chain is 28 into 1000, that you give a 28,000 AMU. Okay, so this is the A will be the right answer. Okay, let's move to the next question. That is the question number 5. In the question number 5, it is similar to the earlier one. In question number 5, the degree of the polymerization in polyethylene is the 50,000, and what the average molecular weight in AMU is. This is 7 lakh, or this is 13 lakh, 14 lakh, or the none of the above. This is the same like the earlier question. Here it is, we haven't told this thing because the number of the mer unit, that is earlier it is the 10,000, no, 1000 only, but we can say the same thing in term of the degree of the polarization. The degree of the polarization, basically same degree of the polarization is the same as the number of mer units in polymer. So we know that the weight of the, or the atomic weight of the ethylene is 28 AMU, as we calculated earlier. 2, that is the CH2 bond CH2. So this will give you the 2 into 24 plus 4 into 1. So this is giving you 28 AMU. Okay, and now the here the mer units are the 50,000. So the total weight will be the average, because they can have the, I mean this is the average value, because mer can have the side branch, or they can have the, so we are average, we are taking the average molecular weight. So this will be the average molecular weight will be the 28 into 50,000. So how much you will get if you multiply this one? So this will come out around 28 into 5, 0, 14, that is the, so this will give you 14 lakh. Okay, so C is the right answer. Okay, you just have to find out how many mer units that are present in your polymer. So if you know the average molecular weight of the one mer unit, then you can multiply that number of mer unit. That will give the total average molecular weight of the polymer one. Okay, let's move to the next question. Question number 6. Sorry. In question number 6, among the following, which example and general formula is correctly related? That is the quartz SiO2n, clay Si2O5 2 negative, asbestos Si2O5 2 negative, and the clay SiO3 2 negative. Okay, so quartz is basically, you know, the silicate. So this is also this is having the same formula unit, that is given as the SiO2, and so this is the correct one. Let's move to the other parts also. In the clay, clay is basically your silicate structure, but clay is also the silicate structure, but the layered one. This structure is the layered one with aluminium in their structure, not just the simple in the structure, not just the simple silicate structure. Okay, So the if I say the clay is having the, for example, the clay having the clonite, having the structure A2Si2O5OH4. This is the layered silicate one. Okay. The asbestos is the silicate miller that, but they are having the fibrous one, and these are having the structure like that Mg3 Si2O5 OH4. So this is for the asbestos, and the third one is the SiO3 2 negative N. So this does not represent the clay one because clay is having the layer structure. So this is not representing the clay one. So the correspond the correct, this is because this clay is having the aluminum in the structure, and they are having the silicate also structure one. So the quartz SiO2 and is the only the correct answer for this one. Okay, the clay this having also having the silicate structure, but this is not the general statement. This is only for the this clonite only. If I talk about the general, so this is not a representation for the general clay one. Okay, so you have to remember few of the examples. So the crystal or the standard crystal, quartz, clay, all of these, and because these are the different kind of the silicate structure. Okay. In question number, sir, now it is because we have the different kind of the silicate structure. So so in question number 7, it is asked which of the following is the orthosilicate. So what are the first thing is what are the orthosilicate, and now we have given the different kind of the silicate. So which of them is will be the orthosilicate one? Orthosilicate are your silicate basically in which your silicon oxygen tetrahedra are isolated, not linked to the, they are isolated. Ortho is they are isolated, they are not linked to the other tetrahedra. So we call the orthosilicate when we are this silicon oxygen tetrahedra is not linked to the other tetrahedral, or the isolated, not connected, or the not connected to the other tetrahedra. Okay, so this first given, this is the same silicate Se2Si2O7. This is your sorosilicate. Sorosilicate, in sorosilicate, what we have the two tetrahedra, that is two SiO4 tetrahedra share the one oxygen atom, because they can be from the only share the one oxygen atom and then give you this Si2O7 2 negative. And so in soro we have the two silicate tetrahedra share the one oxygen. How they are saying? By the corner or the face or the edge one, that's also depend on the type of the silicate one. So in soro one they share the only the one oxygen atom. Next one is the Mg2SiO4. This is the orthosilicate, and where your silicon is in isolated SiO4 4 negative, because we have the orthosilicate and the silicate will be the silicate unit will be the SiO4 4 negative, and this is Mg is only just the cation there is in the that unit. So this is Mg1. So this Mg2 SiO4 is your orthosilicate. In Na2SiO3, this is not the orthosilicate, because this is not having the, if this is the orthosilicate, so this will having the this unit silicate unit SiO4 4 negative, but in this we have the SiO3 2 negative. So it means my one oxygen is also shared here. So this in this is basically this SiO3 2 negative. These are the your metasilicate. We call these are the metasilicate, and they are having the chain-like structure. Okay, and this another one is also, that is MgSiO3. These are also the metasilicate. So the orthosilicate is will be the Mg2SiO4. Okay, so B is the correct answer. Okay, is it clear? Is it clear? Okay. Okay. Look, let's move to the next question then. Question number 8. In question number 8, it is asked, which of the following is the three dimensional silicate? So what are the three-dimensional silicate? We call the three-dimensional silicate is the tectosilicate. That is the tectosilicate. In tectosilicate, we have this silicon oxygen tetrahedra interconnected in interconnected interconnected in three-dimensional framework. Okay, so first one is the hemimorphite, B is the Brill, third is the asbestos, and the fourth is the quartz one. Okay, so hemimorphite is basically the zinc silicate mineral. They are having the sorosilicate. As I told you, they share the double tetrahedral. They in sorosilicate they share the only one oxygen atom, and this is not in the three dimension one. This this hemimorphite, because they share in the, or because they share the one. We have to arrange your tetrahedral in such a way that will give you the 3D framework. Here you can see, from here you can see the, okay, this is having the 3D unit. No, but they are not having. This is the unit cell that is shown here, but it's not the 3D silicate or the tecta silicate one. And the next one is the burl. Burl is the silicose. If you see the structure of the burl, that is the having the cyclosilicate, or which are having in the ring form. They are this silicon oxygen tetrahedral are arranged in the cyclic arrange. So they are this if I choose this tetrahedra, see, this is connected to this way, this tetrahedra, and this if and this connected to this atom. They are interconnected to each other and form the ring-like structure, or the cyclic one, or the circle one, that is giving you, and that is not making the 3D framework. This is not making the 3D framework, because they will, if I see, this is looking like a 2D framework. These tetrahedra are connected in such a way that are forming the 2D framework of the tetrahedra. So Burl is the not the 3D, this 3D silicate one. Next is the asbestos. Asbestos or crystal structure having the different crystal structure, that is depending upon the what of the which kind they are having. So one is the calcotile, that is the most common asbestos. They are having the layer structure. From here you can see this is the layer structure. So this is also the 2D kind of framework, not having the 3D one and framework, and they are interconnected, layered in such a way, and they having the tubular growth or the scroll like growth. The basic unit for this one silicate tetrahedra in the sheet form, because so they are having the 2D framework. Another type of the asbestos is the amphibole. This amphibole group having this parallel chain of, because this is the one chain, this is having the one chain of the silica, and these are the another chain, and they are connected one, and the strength of the because they are connected in such a way, either they are having the either prismatic or the needle like structure one. So this is the amphi base. So these this asbestos having the 2D like framework. In this one we have seen this is the seat one, they having the seat structure, and this amphibial are having the needle like, or this the these are not in the 3D framework, or they are having the chain parallel chain of the silica tetrahedra. Now another it is the this is the quartz one. If I say this is the quartz one is basically tectosilicate structure, because this each oxygen atom is your share between the two tetrahedra. That's why they are, because if I see this oxygen atom, okay, we can see. So that will be this oxygen atom. Let's say this is my oxygen atom. So this is shared by the this tetrahedra, and this oxygen is also shared to this tetrahedra. So this my quartz is having the three-dimensional framework, or we can say this is your tecto tectosilicate. Okay, so how these silicate are arranged? So that's give you the arrangement of your silicate, and the corresponding name are defined for the different of the silicates, and you have to tell if they are arranged in the sorosilicate, so they are the hemimorphite one. And if they are having in the cyclic one, so the burl is this is the one of the example of the burl. So we the category for the this one is the cyclosilicate one. The asbestos also they are having the 2D seat like structure, or they are having the chain in the parallel chain of the silica tetrahedra. You can say this is the one tetrahedra, this is the one tetrahedra, another this one. So they are having the parallel chain, and this is the one chain of the this one chain, and this is the another chain, or they are the parallel one. So they are having the parallel chain of the silica tetrahedra. Okay, or quartz is also quartz is having the 3D framework. So we call it the 3D framework. We call the silicate is the tectosilicate one. Okay, so this is about the question number 8.1. Now let's move to the question number 9. In question number 9, it is the pyrosilicate. That is, pyrosilicate is having the structure Si2O7 6 negative are obtained when we obtained this structure. When the two SiO4 tetrahedra share a common oxygen, two oxygen of each silicate, this is silicate tetrahedra shared with the other, or the three corner of the set this if this is your silicon, and this is your tetrahedra. If I say this one, so this is your tetrahedra. If two tetrahedra, if another tetrahedra is this one, so if it is saying the one common oxygen, or the each tetrahedra share with the two oxygen, if they are the kind of age like structure, so they will share the two oxygen one, or the three corner of the each tetrahedra shared. So we will say this is the our face, I mean the one of the face is shared. So this is your face shared silicate, or the no oxygen is shared with the other. So how in the pyrosilicate, how this is oxygen is shared with the another tetrahedra. So you have to, so we have the different type of the silicate I have attached here. So the in the single tetrahedra, we can see here in this one, if I see this is silicate tetra single tetra, that will be the SiO4 4 negative basically, because according to the charge we have the total charge of the silicate one will be the SiO4 4 negative one. So silica is connected to the another silica, and these oxygen are not connected to the other one. So this is only the single tetrahedra. In the pyrosilicate, they are attached with the now the two tetrahedra. This is one tetrahedra, and another is this tetrahedra. They are connected with the this oxygen. So in pyrosilicate, they are connected with the one oxygen. if I say the view of the I mean the top view of this pyrosilicate, this will look like this way. So this oxygen will be the shaded by the two tetrahedra. If I see in the cyclic silicate, this one tetrahedra, they are arranged in a such a way so that they make a cycle one, the complete cycle of the tetrahedra. This one cycle that's connected to this will be the shape. So in this cyclic one, we can see here because the two oxygen are shared with the another, because if I look at this tetrahedra, so one oxygen is shared to this tetrahedra and this oxygen is shared to the this tetrahedra. So the two oxygen of a single tetrahedra is shared with the two different tetrahedra. In the chain silicate, the silicate are the arranged in such a way they are forming the chain like structure. In here also they are having the two oxygen are shared here, but these are connected in such a way. Let's see here. So the one tetrahedra, second tetrahedra, and the third one, fourth one, same like, so they are making the chain one. So these they are named as the chain silicates one. The mer unit for the chain silicate will be the SI. So remember all the mer unit for the different kind of the silicates ones. For the single tetrahedra, it will be the SiO4 4 negative. For the pyro ones, pyrosilicate, it will be the Si2, because this is the mer unit. Now, because here we talk about the two tetrahedra, not a single one. So this will be the Si2O7 6 negative. In the cyclic one, we have the SiO3 2 2 negative, or that depend upon the mer unit also, and because what how many are the silicate in your one cycle. So that's why the charge is also that depend upon the N also. In the chain silicate, we have the chain like structure, so they are having the mer unit of SiO3 and 2n minus. In the double chain silicate, because here in the chain silicate we can see this silicate are in the form of the chain like structure. In the double chain we have the two chain. This is the one chain and this is the another chain, and they are also connected with this one. So if you can see from here, each of the oxygen of the single, not the each one, the three oxygen of the single tetrahedra are connected to the other tetrahedra. This is oxygen is connected to this tetrahedra. This also oxygen is connected to this tetrahedra, and this oxygen is connected to this tetrahedra. These are forming the double chain. This is the double chain one, because there is the one layer of the chain silicate and the another chain of, in the chain silicate we usually have the two are linked. Now because we have the double chain, so there will be the one chain here also. So this oxygen will also be shared with to the another silicate layer. So this will give you the double chain silicate, and the this will give you the mer unit for this will be the Si4O11 and 6 and negative. And the sheet like structure, we have the note, this is not confined to the only the two layer of the chain silicate, we have the different sheet. So each one, so this is this layer is connected to this one, and again this layer is connected to this one. So there is the multiple repetition of the chain silicate in the layer form. So different will be the, so different kind of why this is. So there are the different kind of the silicate one. So single, pyro, cyclic, chain, double chain, and the seed silicate one. So in here it is asked if we have the pyrosilicate, that is the Si2O7 6 negative. It will obtain when two SiO4 tetrahedra share a common oxygen, two oxygen of each SiO4 tetrahedra share with the others, or the three corners of the each tetrahedra share, or the when the no oxygen is shared. When the no oxygen is shared with the other, that is your single tetrahedron. When your three corner of the each this SiO4 tetrahedra are shared. So three are three oxygen. Now the three oxygen, if you see, the three oxygen are shared here in the double silicate or the in the seed-like structure. So in them the three corner of the each silicate tetrahedra are shared. In the if I look at the B part, that is given the two oxygen of each silicate. Yes, the two oxygen of the each silicate is shared in the cyclic one or the chain silicate one. So this belongs to the cyclic or the chain silicate. Now in the first, the two SiO4 tetrahedra share a common oxygen. Yes, in the pyrosilicate one, this oxygen atom is shared with the two tetrahedra. So the in pyrosilicate, two silica tetrahedra share a common oxygen. So A will be the right answer. Okay. So these are the different type of the silicate one. How they are arranged? So their naming are corresponding to that. Okay, so you have to also remember the MER unit for the different kind of the silicate one. So this is all about the question number 9. Let's move to the question number 10. Now we have the muscovite belong to which category of the silicate? So as I already told you, they are so this is the one of the member of this muscovite. It belongs to your mica group. And mica group, basically they are having the seat like structure, and they also in the following examples we have the one is the pyrosilicate, ring silicate, orthosilicate, and the seed silicate. So in the pyro we already told there's the one oxygen, that it's not like the seed structure. So ring is also not the seed structure. Ortho is also not a seed like structure. Seed silicate is basically the your silicate are in the seed structure. So your muscovite belongs to your seed silicate, and that is having the MER unit is Si2O5 2 negative, and you can see here also. So remember the corresponding MER unit for this one. So if you know they are of what kind of the structure they are having, so you can find out the category to which they belong to. Okay, so this is question number 10. Let's move to the question number 11. In question number 11, what is the coordination of Zn2 positive Si2 negative in the crystal structure of the wurtzite R? So you know this is your wurtzite one. You know about the wurtzite one. So this is the wurtzite one, and as the professor already told you, wurtzite having the MS stoichiometry, and they are having like ZnS, ZnO, silk carbide one, because if you see from here, these anion is basically if I say Zn in ZnS will be the Sn2 negative, in ZnO will be the O2 negative. They are forming the this HCP one. You can see from here all these anion are at the corner of the hexagonal one, at the center one, there is a plane at the center one, this one, this one, this one, and also at the bottom layer of the hexagonal. So they are making the HCP lattice with half of the tetrahedral side with the cations one, because we have the Zn is the your cation one, half of the tetrahedra, this is the tetrahedra side that are filled by the cation one. So they are making the anions are packed in the form of ABAB. So the if you see this structure, see from here, if you look at this structure, so you have to find out the coordination of the Zn2 positive and the S2 negative. So the what will be the coordination? Coordination number is the number of the nearest neighbor of this Ni. If it is asked about the Zn2 2 positive, so how many number of the nearest number of the nearest neighbor of Zn2 positive? If I say this yellow is your Zn2 positive, and this gray color is giving you the S2 negative. This is the for the zinc sulfide, because zinc sulfide in exists in the two form, mostly in the wurtzite on the zinc plate one, the yes. So in this one, so if you see look at this zinc atom. If I say this zinc atom, this is my zinc atom. So it is attached to how many of the oxygen atom? No, the sulfide atom. This sulfide atom connect to the this one. This is one. This is connected to this one, and this is connected to this one, and this is connected to this one. So this is in the tetrahedral form. So this the coordination number for the zinc 2 positive will be the is the 4. So similarly, what will be the coordination number of the sulfide one? This is the S2 negative. Look at the one sulfide and check the how many zinc are connected to this S2 negative. That will be the coordination for the S2 negative one. Okay, let's see, this is your sulfide. Now see, this is your sulfide one. This is S2 negative. Now check how many Zn2 positive are connected to this sulfide one. That will be your coordination number. Check one and tell me how many will be the what will be the coordination number for this S2 negative. So what will be the coordination number for this one? This is connected to this one, this zinc one, and this C. This is the your one of the tetrahedra. So what will be the coordination number for this one? This is not connected to this one, this atom. So this is only. So how many zinc atom are connected to the S2 negative? This is the one, second, third, and fourth. So the coordination number will be the also for the sulfide S2 negative will be the 4 one. So the coordination number for the zinc 2 positive and the S2 negative in wurtzite ZnS will be the 4 and 4. So A will be the right answer. Okay. Yes, A is the correct answer. 4 and 4, the coordination number for the Zn2 positive and the S2 negative. This your wurtzite having the stoichiometry of Mx in the form of Mx. Let's move to the question number 12. So now in question number 12, in corundum, oxide are arranged in the HCP arrays, and the aluminium ion occupy the 2 by 3rd of the octahedral words. What is the formula of the corundum? So if I told you, so in corundum we have the oxide ion and the aluminium ion. So there will be the combination of the aluminium and the oxygen. How they are connected? What is the stoichiometry of the aluminium and the oxygen one? This you have to find out. So what will be the stoichiometry for the aluminium? How many aluminium in the 1 unit cell, or how many of the oxygen in the 1 unit cell? That we have to find out. So your oxide ion are in basically arranged in the HCP arrays, and we know in HCP array we have the, and they are arranged in the octahedra words. In the octahedra words, how many are the octahedra words in the HCP lattice one? So octahedral words is the twice the number of your oxide ions. It's twice the number of your oxide ion, and it is given here also this aluminium 3 positive occupy 2/3 of the octahedral words. Now the octahedral words, it is occupying the 2/3 of only, and octahedral is twice the number of the oxide ion. So number of the aluminium ion will be, they occupy the 2/3 and they are octahedral either twice the number of the oxide ions. So this will be the 4/3 one. So number of the oxide ion if I say, and if I make it this to the simple, so let's connect for the 3 oxide ion, we have the 3. For the 3 oxide ion, if we have the 3 oxide ions, so number of the octahedral or octahedral word will be the 6. So number of the aluminium ions, ion will be the 2/3 into 6, that will give you the 4 one. So aluminium ion are, aluminium 3 is positive, your 4, and oxygen is your oxygen, or your this is O2 negative is basically your 6 one. So how they are arranged? So if make it the smaller fraction, so this will give you the 2 3. So aluminium 3 positive is 2, O2 negative in the form of 3. So what will be the chemical formula? So chemical formula will be Al2O3. So this is the chemical formula of aluminium oxide. So aluminium oxide is your corundum. Okay. So how you will proceed with this, because it is given your oxide ion are arranged in your HCP array, and aluminium ion occupy your the 2/3 of the octahedral words. So we know that they are in the octahedral. So octahedral words is the twice the number of the oxide ion. So they are occupying the 2/3 of the octahedral. So number of the aluminium ion will be the double of that thing. So this will give the 4/3. Now if we assume, because this is in the form of the fraction one. So if I'm making it simpler one, so for consideration for the we have consider the 3 oxide ion. So for the corresponding 3 oxide, number of the octahedral void will be the twice, because that octahedral voids are the twice of the oxide ion. So this is giving you the 6 one. So so now we have the 6 total of the octahedral voids now. But the aluminium, as it is mentioned in the question, this aluminium occupy only the 2/3 of your octahedral. We have the 6 one, but it occupy only 2/3 one. So this will give you the 6, the 2/3 of 6. So this will give the 4 aluminium ion. So there will be the only the 4 aluminium ion will be there. So we have the 4 aluminium with the with corresponding to the 6 oxygen atom. So if I make it simpler, so if we divide by 2, so that will give you the simple 2/3. So the aluminium that are present in the 1 unit is 2, and the oxygen ion that are present in 1 unit is the 3. So they give you the stoichiometry of this aluminum oxide will be the Al2O3. So this is the chemical formula of the corundum. Okay. So this is the, once you know the how they are arranged, how many octahedral words, and you know the how much of the octahedral word will be the occupy the aluminium ion, then you can calculate the what is the stoichiometry in which this aluminium and the oxygen ion are arranged one. Okay, so this is all about the question number 12. Is it clear? Because it is simple one. First you have to find out the how many oxygen ions there, how many the oxygen, how they are arranged. So how many are the octahedral the words are present in that, and the how this your aluminum that the cation is arranged in the octahedral words, so that you can calculate the stoichiometry of this your aluminum oxide one. Okay, so this is all about the question number 12. Let's move to the question number 13. Now we have the ilmenite structure that is having the AbO3, where your oxygen anions form the HCP lattice and the both cation occupied the void. What would be the proportion of the cation filling the void? So how they are, this cations are filling the voids. So you know this AbO3. So this one of the example of the ilmenite structure, that is the FeTiO3. In O3, this is oxygen anion is forming at the HCP lattice, and this A and B are occupy the void one. You know that in HCP we have two tetrahedral words that we have already done in the earlier assignment. Two tetrahedral words and the one octahedral words. So our cation, this is Fe and Ti, or we can say this your A and B will occupy either the tetrahedral words or the octahedral words, and in HCP we have the two tetrahedral words and the one octahedral. So they have to occupy one of them. I mean either the tetrahedra, we have only the three kind of words here, two tetrahedra and the one octahedra. So how they are arranged? So in the first part, if you see, they have said the both the cation occupy the 2/3 of the both the cation occupy 2/3 the octahedra. If you know about the structure, ilmenite structure in the hexatetra, how they occupied, so you know about this. If you see in the figure also here, so this your how are your this Fe and titanium that are arranged or you occupied. You can tell from this one. So in the B part, they both the cation occupying the 2/3 of the tetrahedral. In A part, they have the same occupying the octahedra. In C part, A occupied the 1/3 of the tetrahedral and B occupy the 1/3 of the octahedral. In D part, B occupy the 1/3 of the tetrahedral and A occupy the 1/3 of the octahedral. So which of the following is the correct from this one? You have to tell. So this will be the, if you look at this figure, this is the crystal structure of, let's say this is the FeTiO3, your A is the Fe and B is your titanium and the oxygen O3 is there. So you have to see how this Fe and titanium are occupied. If you see, this is the one of the octahedral. These are the single unit of Fe, how the Fe is arranged, or the titanium, how this is the arranged, and this is the crystal unit structure, the total one. If you see from here, this is red one is your oxygen, this is blue one is the your titanium, that is the titanium 4 positive, and golden is the Fe 2 positive. So this, if I look at this one, this is the golden one, this is connected to how many oxygen atom are? This is arranged in the If I see this is arranged in the four in a plane, or I guess one will be the one will be the, because they are four in the plane. In the, we know that in the octahedra, we if I look at this one, if you can see from this one, this is having the four. One is there, one oxygen atom. Second is here, third is here, fourth is here, one above oxygen atom, another below this atom. So this Fe atom is connected to your 6 oxygen atom. That is why it is written here FeO6. And similarly, if you see the titanium one, so the in the titanium also, this titanium atom, this titanium is connected to the one oxygen, is it is here, another is this one, this one, this one, and this one, and this one. So this titanium 4 positive also connected to your 6 oxygen atom. So it is clear, this is your Fe and titanium both occupy your octahedral, occupy the octahedral voids or your position one. Okay, so from the crystal structure you can see both are having the, both occupy the octahedral structure. Uh, so A can be an answer. So in the B, they are occupying 2 by third of the tetrahedron. No, both are occupying the octahedra. If you look at the C and D part, also A occupy the tetrahedron. No, nobody is occupying the tetrahedral. So C is also not the right answer. B is also not the right answer. And if I look at the D also, so in D also B occupied the 1 by third of the tetrahedra. So it is also not the same case. So B, C, D are not the same case. And you know that this in of the tetrahedra, there are the some are the empty octahedra. So both the occupying only the 2 by third of the octahedral one. Because of the stoichiometry, to confirm that, so they will occupy only the selective, they are only the sum of the octahedral words. So they occupy only the 2 by third of the octahedral word. So both the cation, this your Fe and titanium, Fe2 positive and titanium 4 positive occupy your 2 by third of octahedral words. So your A is the right answer. Okay, so this is the about question number 13. Let's move to the question number 14. So in question number 14, it is based on the sharing of the polyhedra, corner, edge, face, in each case of the silicate SiO4 4 negative, which is or are the correct statement. The radius between the Si and Si face less than the radius between Si and Si edge, less than the radius, this is silicon silica is lesser than the corner. In B part, that the cationic repulsion is minimum in radius, that the distance, or the we can say the distance between the silicon and silica bond, and in corner case, and the cationic repulsion is maximum in the the distance between the silicon and the silicon bond in the face polyhedra. And in the D part, this distance between the silicon and the silica face is greater than the distance between the silicon and silica bond is, and that is greater than the distance between the silica bond in the corner. So what are these three type of the polyhedra? One is the corner one, another is the edge one, and the face one. Let's see. So in silicate one, this is the one SiO4 4 negative. This is the one of the tetrahedra. And how they are arranged? This is my silica atom. One is, this is my silica atom. and these are the my oxygen atom. If I say this is like this way, this is O, 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 and this is your silica one. Now this is the one of the my tetrahedra. Okay, so the my silicon is as sitting at the tetrahedral word, that is the space between this of the tetrahedra. So there my silicon is sitting there. So in the corner one, how this is one? So one of the oxygen is, let's say this is my silica, and this is my oxygen, 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 and the oxygen. So this oxygen is my shared with my in the another tetrahedra. So if this is so these are these one this tetrahedra, these are connected with the corner oxygen atom. So this we call this as the corner polyhedra, because your one of the oxygen is the connected to the another one. In the A's one, now we have the same this structure of the polyhedra. This is your silicon, oxygen, sorry, this is oxygen, 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 oxygen. Now this your A's, if I am saying, look at this way, this A's is connected to the another silica hedra. How this will be the, I mean, let's say these are the two, another silica here. Go somewhere here. I mean, oh, this A's is shared with the, if I look at this A's is shared with the another tetrahedra. So this will be the your, this is not the exact one, but it will be the somewhere like the this A is one, the two oxygen atom will be the, if I look at these one, we can say there the A's are shared, this in the, that question. Here you can also see that this A's is shared with this one. This is S, or the completely, if I say the another one, if there is one tetrahedra here, the silicon is sitting here, so this A's will be shared here, somewhere like this thing. If this is the kind of thing, so there will be this, that will be the case for the A's polyhedra, or next for third one is the phase one. In the phase one, the one of the phase, if there is your silica atom sitting somewhere here, so this phase is shared with the another polyhedra also. The one of the phase will be the shared this one. It means your the three oxygen atom will be shared to the other polyhedra. In the A's one, two oxygen atom of a single tetrahedra is shared to the other tetrahedra. In the corner one, the one oxygen atom is shared with the or they are connected with the corner one. I mean the two, we have the different two polyhedra. If they are connected with the corner one, that is the corner one, corner polyhedra. If they are connected with the edge, so that will be the edge polyhedra. And if they are connected with the face one, so that will be the face polyhedra. As face and the corner one. These are the three types of the polyhedra. So in the given option, it is said that this in the phase one, the distance between the silica and silica bond, this silica and this silica, if this is the phase one, so another phase, same this phase is shared, so this will be the another, and it will be like somewhere this way. So this one of the phase is shared. So the distance between them, the distance between the silica and silica bond in phase is smaller than the distance between the silica and silica bond edge, and the say is smaller than the r distance in the corner. Yes, from this we can see that if we have only connected with the corner one, so there is a huge distance between your silica and silica. So distance in the this corner one, this r distance between to the silicon and the silicon bond is larger as compared to the this one, because it is connected to this edge. Now your this polyhedra, the another this tetrahedra is come closer to this one, to the first one, because they are shared with the edge one. Now so the distance between this r silicon and silica atom, the bond between the silicon and silicon atom get shorter. Okay, for the this for the edge one. If I talk about the face one, now the my polyhedra come to face, they are completely joined. They are making a 3D. I mean the this like structure. This is the one of the face is shared with to the another one. So now they are the distance between them is much closer as compared to the edge and the corner one. So your R, the distance between the silica bond in the phase one will be the smaller one, that will be the smallest one compared to the your R, the distance between the silica bond in case of the edge, and that is also smaller to the distance between the silica bond if I talk about the corner one. So so this is the case between the silicon and the silicon bond, the distance between the so A is the same thing, A part is having the same thing, so your A part is the correct answer. Okay, now move to the B part. In the B part, it is asked the cationic repulsion is minimum in the corner. They are because your silica atom, because the distance between the this corner silicon bond in the corner polyhedra is maximum, so there will be the less repulsion. So less repulsion, that is basically less cationic repulsion, because silicon and silicon they are far away, so there will be the less cationic repulsion. So yes, so B will also, okay, just a second. Okay, so your B will also the correct answer. The cationic repulsion is minimum in case of the corner one. In the C part, it is asked that the cationic repulsion is maximum in the R distance between the silicon and silicon bond if it is the phase center. Yes, they are the silicon and silicon bond length is smaller in the case of the phase polyhedra, so there will be the more repulsion between the cation atom. So C is also the correct answer. So thing is there, I mean the distance between the two cations, how they are how they far, I mean if they are closer, so there will be the more repulsion. If they are far away, so there will be the less cationic repulsion. So in phase we have the they are the closer, I mean the distance between the silica atom are is not that much compared to the corner and the edge one, so the repulsion will be the maximum in case of the phase polyhedra. In the D part, it is said that the distance is larger. This is the opposite to the A part, no, but this is the order is in the reverse direction, not in the same one. So D is not the correct answer. A, B, and the C is only the right answer. You know, I mean, if my one of the polyhedra is connected to the another, how they are sharing? If they are only connected with the, with the only a single point, corner atom it may a single point. Now they are freely, thus they have to connect with the only single atom. So they are kind of free one. There will be the this silica and the another silica. They are having the larger distance. If they have the condition, one condition is there, they have to connect with this edge. Now the one of the edge, I mean the this atom, they now the two oxygen atom are fixed one for the both the polyhedra. Now there is the another, there is the free only the this two oxygen atom are the free. So there are the particular arrangement for this one as one also. If it is talk about the phase one, if one is the phase fix, one of the phase of the polyhedra is fixed one. Now another also sharing the same phase. So the I mean there is only the one possibility of this polyhedra. Neither one possibility. There are few random possibility of this polyhedra because one of the phase will be the fix. Another they have to arrange because the three oxygen atom will be the share in case of the this one oxygen atom. They have to also take care of the angle between this polyhedra one because you have to take you the I mean the this polyhedra have to I mean the fully the bond angle also the angle is the 109.5 something now. So the angle between them it should be, but one face is fixed. So the three oxygen atom is shared with your another polyhedra. So there is one oxygen that will only occupy the one position. So that's why the distance between the silicon and silicon in the this phase polyhedra will be the less compared to the edge one and compared to the corner one. Okay, and similarly, your cationic ripples, if they are closer, so the cationic repulsion will be the maximum. If they are far away, so the cationic repulsion will be the minimum one. Okay, so corresponding A, B, and C will be the right answer for this one. Okay, is it clear? Hopefully, it is clear. It is not that much typical. You have just to think how they are arranged, so it will be clear to one. Now let's move to the question number 15. In question number 15, what kind of the which among the following will have the maximum softening temperature? Pyrex glass, Vicor glass, fused silica, and the window glass. So what kind of these glasses are? Let me tell you first thing, and then we will discuss the are they having the which of the following having the maximum softening temperature one. If you see this one, the Pyrex glass is made up of the 80% of the silica, 14% of the borate, this is the B2O3, and the 4% of the sodium oxide, that is the Na2O. So the softening temperature is basically around the 550 degrees Celsius. In the Pyrex glass, we have the borosilicate. If we said this is the borosilicate glass, and they are also having the low thermal expansion and the good resistance. This Pyrex glass are the good resistance to your thermal stress because they are the 80% mixed with the 14% boron oxide, P2O3, and the 4% of the sodium oxide. In the Vicor glass, the silica amount is higher and there is no sodium oxide. So the silica is your we know this has having the higher this softening temperature. So if you see, because here the amount is greater than this one, so your softening temperature also increases for the Vicor glasses. In Vicor glasses, this temperature and they because they are having the high this softening temperature, so they are having the higher excellent thermal and the chemical resistance because they are higher, so they can resist to the chemical and the thermal condition up to this 1100 degrees Celsius, because they will get softened after this temperature. I mean, they add around 1100, they get softened. So before that, they can resist to the thermal and the chemical resistance. So they are excellent resistance compared to this the Pyrex one. They have the excellent thermal this thermal and the chemical resistance. So in the another one is the window glass, the fused glass. We third part is the fused glass. Fused glass is made up of the pure silica. This we have also discussed in the fused glass is made up of pure silica. So they have the higher softening temperature and the because they have the higher, so they have the low thermal expansion. See, your thermal expansion depend upon your temperature, softening temperature one. Next one we is the another is the window glass. Window glass generally we see that is the soda lime glass, also we call it the soda lime glass, that are having the low softening temperature, and they are also having the temperature in the range of the 120 degrees Celsius. After that they get kind of the mold. They get mold, I mean, they get softened or they hit it, they melt, or we can say this is the softening temperature. In window glass we have the 9% of the calcium oxide, 4% magnesium oxide, 14% the sodium oxide, and 1% is the alumina, and the remember is your the silica. This is the SiO2. Remember one is the alkyl. So these are the four different type of the glass: Pyrex one, the Bicore, window, and the fused one. The fused one is almost having the pure silica. Window they are only they are having the uh, compared to the others, they are this, if I say the second number with the Vicor glass, third one is uh, uh, for the Pyrex one, and window glass is having the less silica oxide one. So the softening temperature, because they are having the less silica amount in their window glass, so the this the softening temperature for the glass, if I see, based upon this will be the lower, or the this in the so let's move to the question. I mean, which of the following having the maximum or the lower the this okay, the maximum softening temperature. So if I talk about the this lower softening temperature will related to the your lower with the less content of your silica. So the less content of silica is your in basically in your window glass. So if it is asked for the lower softening temperature, then it will be the window glass. Here it is asked about the maximum softening temperature. So maximum softening temperature will lead to having the maximum, I mean the glass having the maxima of your silica, this is your SiA2, and we already told you that the fused glass silica, or your fused glass or your silica is having the almost pure of the silica. So this is having the maximum softening temperature. So fused glass is the having the maximum softening temperature, and the window glass is having the lowest, I mean the minimum softening temperature. This is around the 120 degrees Celsius, and this is having the around maximum. I don't know, Vico glass is having the 1100 degree, and this is the 550 as we have seen it here. Okay, okay. Now this is all about the question number 15. Now let's move to the next question. That is the question number 16. Okay, so in question number 16, and this is the last question, I guess. So, which of the following result in an increase in the melting temperature of the polymer? So, how your, because we have already discussed the thing, the how the amount of your silica is present in your glass, so that also correlate with your melting temperature or the softening temperature of the glass one. So, of the But here it is asked about this silica is also a, if I'm talking about the silicate one, so there is also that is the polymer one also. So silicate are the different polymer units, so that is the silicate. So so if I talk about the polymer one, the polymer, how the melting temperature of the polymer is affected by, if the presence of the, so you have to increase in the vessel, so falling can increase, so increase in the melting temperature there, if the polymer is tightly, there is the regular arrangement of the matter. If I say regular, because it's hard to the to melt the temperature to make it flexible. If your polymer is flexible, or I mean, if you can kind of that is easily having so that you can easily break now. So if that is having the only single bond between them, so you can easily melt it. If they are the double, and so it also depend upon the what kind of the bonding in your polymer, is it the single bonded or the double bonded or the triple bonded, so that will lead to your melting temperature one. So how tightly they are bonded, basically that's give you the this melting point criteria. If they are tightly bonded, so the melting point will be the higher. If they are not loosely bounded, so the melting point for the that polymer will be the lower one. So if I say in the first study they have asked the presence of the double and the triple bond. So if the material is the presence of the double and triple, yes, the presence of the double and the triple bond can lead to the increase in the melting temperature of the polymer, because they give the strength to that polymer, and that's why your this melting temperature will get increased. So the presence of the positive double and the triple bond lead to the increase in the melting temperature. Another, the presence of the large and the bulky side groups. Yes, if they are the large and bulky, they if they are the large, and also that will also lead to the increase in the melting temperature, that will take time, or that will be the resistance to your temperature, this temperature. So uh, that's why they will increase the melting temperature of that polymer one. So the presence of the large and the bulky side group also lead to the increase in the melting temperature. In the same part, if the branching of the polymeric chain, if there is polymer, there is another branching, so if you get the temperature, that branch will I mean, if you give the some temperature, then at a certain point the branch of that will get more melt, so that the branching, if there is the only single one, so there is no branching, so there will be higher chance of the high melting temperature. But if there the branching of exists in the polymer, so the branching will lead to the decrease in the melting point of the polymer. And the absence of the any side group, I mean, absence of the any side group, there is no side group, there is only the carbon chain, so that's also not increased to the melting. How they can increase, I mean, the question is how they can increase the melting point. So the if the presence of the double and triple bond, that can increase to, and if there is a presence of the large and the bulky side group in the polymer, so that will also increase the melting temperature of the polymer. So A and B the correct answer for this one. Okay, now there is something, this glass, about the glass, different kind of glass we have already discussed. There are different long chain polymer, that is the ethylene based, that is the polyethylene. In the polyethylene we have the all the this carbon and carbon are attached to the your hydrogen one. In the PVC, one hydrogen is replaced with the your Cl, and because in the polyethylene, that application are the bags, container. PVC that we use, PVC we call na PVC pipes and all that. So PVC tubes and the pipes that use in the one hydrogen is replaced with the chlorine. In third, the PP one. So in the polyethylene, one is one hydrogen is replaced with the CH3 group, so that is used in the bumpers, dashboards, and the buckets one. In the polymethyl methanol acrylate, and the this one hydrogen is replaced with the CS3, and the another is the with the acrylate, that is the CS3COO. So this is the another is replaced with the CS that is used in the window on the plexiglass. Another is the polystyrene, that is in one hydrogen is replaced with the C6H5. So these are the long chain polymer that is based on the ethylene 2 carbon one. And also there are the different kind of the silicate one here. This is the nesosilicate. Here your composition unit is SiO44 negative. Sorosilicate, this is Si2O76 negative. This is like this way. Cyclic one we have already discussed. Inosilicates, that the single chain we already discussed. The single chain we call it the inosilicate one. The composition unit is here, and the example is the MgSiO3. So these are making the single silicate, and the inosilicate, this is the double one, because we have discussed the single chain also, or the double one same is this thing, but here the single chain in the double chain. Like the phyllosilicate are arranged in the such a way. I mean, this is the form the one seat-like structure, of we can say this is the seat-like structure. Mica is also, this example is mica. Mica is also the seat-like structure, the layer structure, and the tectosilicate, that is having the three-dimension framework, or the three-dimension, the silicate are arranged in the three-dimension one. You can see here, this is the three-dimension one. So these are the different kind of the silicate one. How they are arranged, the structure linkage schemes among the silicates. So their naming are based on their structure linkage. So this is all about the assignment number 6, as we have mostly discussed about in the silicate here, and the polymerization, how the this your mer unit, what is the mer polymer is, the mer is basic unit of your polymer is basically repeating of your mer unit. So we have discussed silicate and the polymer in this assignment number 6. In first question, we have discussed about we have to identify the mer unit and the corresponding category. We know this is the your polychloro trifluoroethylene, and that lead to the different category of the thermoplastic one. And the second, we also have to find out the mer unit, that is what we call the site unit, the polyvinyl one, chloride one. And the another, what are the factors that are responsible for the non-crystallinity in the polymer. In the question number 4, we know the atomic average atomic this mass unit of the ethylene, and if we have the 1,000 number of mer units, so what will be the weight of that polymer? Or if we say this is the, if the degree of the polarization in the polyethylene is this one, it is the same as the number of the mer units, so we can calculate the average molecular weight of the polymer one. In the sixth one, what are the quartz, how the silicate are arranged, what different type of the silicate we have to discuss. Silicate also. In the eighth one, we have discussed about the three-dimension silicate. So which of the following are the three-dimension? Some are the two-dimension sheet-like structure, and so that's why three-dimension. In the what are the pyrosilicate? Pyrosilicate with how they are structurally linked. So the two tetrahedra are interlinked with the with one oxygen, that is in the pyrosilicate one. In the this is the in question number 10. This is the Muscovite, so this is one also the mica. This is the lay that is forming the seed-like structure. So this belongs to seed silicate one. Question number 11. What the wurtzite? Wurtzite. What is the coordination of both the zinc and sulfide in the wurtzite? And the what is the formula of the coordinum? So that is the because we already know this oxide ion are present in the arranged in the HCP array. We know the how many octahedral words in the HCP array, if it is, and it is in the question it is given how the aluminum occupy only how much of the octahedral word, that is a 2 by 3rd. Once we know that the number of the oxide ions, so we can calculate the chemical formula of the quantum. Okay, so this is about next question. It is asked about the ilmenite structure AbO3. So how your oxygen and this cations occupy the this mm, structure occupy the position in your in the unit cell. So your oxygen occupy the HCP lattice, and the both the cation occupy the octahedral, that is a 2 by 3rd of the octahedral words one. In question number 14, that's how the what is the relation between the distance between the silicon distance between in the face polyhedra, is polyhedra, and the corner polyhedra. In this one, how the your maximum softening temperature related to the SiO2. The maximum amount of SiO2 lead to the maximum of softening temperature, and the lesser amount will give the less softening temperature. In 16, how this melting temperature depend upon the what of the following which of the following condition lead to the increase in the melting temperature of the polymer. So double, of course, the double and the triple bond will lead to the increase in the melting temperature, and the presence of the large and the bulk side group also lead to the increase in the melting temperature. So this is all about the question assignment number 6. So if any one of you have any doubt in the assignment number 6, so we can discuss it. So if you have doubt, just unmute yourself and you can, sorry, you can ask. So if you have doubt, if you have any doubt, just let me know. Okay, age of you, I don't know. Okay, so no doubt. So okay, is it clear? Yes. Okay, if so, this is all about the question number. This is the assignment number 6. We will discuss the assignment number 7, hopefully in the coming Friday. Hopefully, I have some work, so I will take the assignment 7 on the Friday and the 8th on the Tuesday on. Then we will finish with this coursework. Okay, so that's all with the assignment number 6. If you have any doubt, email me either on the put your question on the Google form. We will respond you accordingly. Okay. If you don't have, you can leave the meeting. We will discuss the next assignment in the next classroom. Okay. Okay. Not this way. Okay, Kalpana, if you have any doubt, either you can mail me or you can put on the doubt on the Google form. I will respond you accordingly wherever you put your doubt. Okay, thanks for the meeting. Thank you. Thank you, everyone.